Let's do another example. So what I want to do is define what it means for two matrices to be similar. Okay. So we say A is similar to B. These are two matrices if there exists an invertible P such that B is equal to P inverse A and then P. Okay, and this is the same thing if I multiply on the left by P and then on the right by P inverse. This is the same thing as saying P, B, P inverse equals A. Okay? So A is the same as B, but I have to multiply by P and then P inverse. Okay, so here's a theorem that relates similar matrices to eigenvalues, because that's the topic of this chapter, eigenvalues. So the theorem Okay, so if I have two matrices that are similar, then they have the exact same eigenvalues. So let's try to prove this. And I'm going to prove it using the characteristic equation. So let's say that lambda is an eigenvalue of A. So by the characteristic equation, the determinant of A minus lambda times the identity is equal to 0. Okay, so I'm assuming, assume that A is similar to B. So what I want to show that the determinant of B minus lambda times I is also 0 for the same lambda as up here, right? Because I've assumed that lambda is an eigenvalue of A, and I want to show that lambda is an eigenvalue of B as well. Okay? Okay, so what does it mean to be similar? Well, I know that B is equal to P inverse A P. Right? Okay. So this is for some Okay, so let's look at b minus lambda times the identity. So b minus lambda times the identity is equal to, well, if b is equal to p inverse AP, I'll just replace that. So I have p inverse AP minus lambda times the identity. Okay. So if p is invertible, I know that the identity matrix is equal to p inverse times p. Remember, this is the definition of an invertible matrix. The inverse times the matrix equals the identity, right? So I'm going to replace this by p inverse p. So this guy equals p inverse A p minus lambda p inverse p. Okay, now I'm going to factor out p inverse. So this is equal to p inverse times A p minus lambda p. So that's factoring out p inverse on the left. And now I'm going to factor out p on the right. So I got p inverse A minus lambda times the identity p. Okay, now I'm going to take a determinant of both sides. Okay, so we'll take determinant. Determinant of the left side will equal the determinant of the right side. On the left side, I've got b minus lambda I, and on the right side, I got p inverse A minus lambda I p. This is a product, so remember that the determinant of AB is determinant of A, determinant of B. So I can split this guy up into a product of three determinants. So this is equal to determinant of P inverse, determinant of A minus lambda identity, and then determinant of P. Okay, now I'm going to use that determinant of P inverse is 1 over determinant of P. Okay, so this is equal to 1 over determinant of P times the determinant of A minus lambda identity times determinant of P. The determinant is a number, right? So this is a number, maybe it's 5, and this is 1 over 5. So they cancel out. So I get determinant of A minus lambda identity is equal to determinant of B minus lambda identity. Right? Now I've assumed that this is equal to 0. So this guy has also got to equal 0. So this shows that A and B have the same eigenvalues.